Methane is a chemical compound with the chemical formula CH4. It is the simplest alkane and the main component of natural gas. The relative abundance of methane on Earth makes it an attractive fuel, though capturing and storing it poses challenges due to its gaseous state found at standard conditions for temperature and pressure. In its natural state, methane is found both below ground and under the sea floor, where it often finds its way to the surface and the atmosphere, where it is known as atmospheric methane. History. In November 1776, methane was first scientifically identified by Italian physicist Alessandro Volta in the marshes of Lake Maggiore straddling Italy and Switzerland, having been inspired to search for the substance after reading a paper written by Benjamin Franklin about flammable air. Volta captured the gas rising from the marsh, and by 1778 had isolated the pure gas. He also demonstrated means to ignite the gas with an electric spark. Properties and bonding. Methane is a tetrahedral molecule with 4 equivalent CH bonds. Its electronic structure is described by 4 bonding molecular orbitals resulting from the overlap of the valence orbitals on C and H. The lowest energy Mo is the result of the overlap of the 2s orbital on carbon with the in-phase combination of the 1s orbitals on the 4 hydrogen atoms. Above this level in energy is a triply degenerate set of MOs that involve overlap of the 2p orbitals on carbon with various linear combinations of the 1s orbitals on hydrogen. The resulting 3/1 bonding scheme is consistent with photoelectron spectroscopic measurements. At room temperature and standard pressure, methane is a colorless, odorless gas. The familiar smell of natural gas as used in homes is a safety measure achieved by the addition of an odorant, usually blends containing tert-butaldiol. Methane has a boiling point of -161 degrees Celsius at a pressure of 1 atmosphere. As a gas, it is flammable over a range of concentrations in air at standard pressure. Solid methane exists in several modifications. Presently 9 are known. Cooling methane at normal pressure results in the formation of methane I. This substance crystallizes in the cubic system. The positions of the hydrogen atoms are not fixed in methane I, i.e., methane molecules may rotate freely. Therefore, it is a plastic crystal. Chemical reactions. Main reactions with methane are combustion, steam reforming to syngas, and halogenation. In general, methane reactions are difficult to control. Partial oxidation to methanol, for example, is challenging because the reaction typically progresses all the way to carbon dioxide and water even with incomplete amounts of oxygen. The enzyme methane monooxygenase produces methanol from methane, but cannot be used for industrial-scale reactions. Acid-base reactions like other hydrocarbons. Methane is a very weak acid. Its pKa and DMSO is estimated to be 56. It cannot be deprotonated in solution, but the conjugate base with methylithium is known. A variety of positive ions derived from methane have been observed mostly as unstable species in low-pressure gas mixtures. These include methanium or methyl cation CH+3, methane cation CH+4, and methanium or protonated methane CH+5. Some of these have been detected in outer space. Methanium can also be produced as diluted solutions from methane with superacids. Cations with higher charge, such as a CH2+6 and CH3+7, have been studied theoretically and conjectured to be stable. Despite the strength of its CH bonds, there is intense interest in catalysts that facilitate CH bond activation in methane. Combustion. Methane's heat of combustion is 55.5 megajoules per kilogram. Combustion of methane is a multiple-step reaction. The following equations are part of the process, with the net result being CH4 plus 2O2 CO2 plus 2H2O, CH4 plus M asterisk CH3 plus H plus M, CH4 plus O2 CH3 plus HO2, CH4 plus HO2 CH3 plus 2O, CH4 plus OCH3 plus H2O, O2 plus HO plus O, CH4 plus OCH3 plus O, CH3 plus O2 CH2O plus O, CH2O plus OCH plus O, CH2O plus OCH plus H2O, CH2O plus HCO plus H2, CHO plus OCO plus O, CHO plus OCO plus H2O, CHO plus HCO plus H2, H2 plus OH plus O, H2 plus OH plus H2O, CO plus OCO2 plus H plus O plus M H2O plus M asterisk, H plus MH2 plus M asterisk, H plus O2 plus MHO2 plus M asterisk. The species M asterisk signifies an energetic third body, from which energy is transferred during a molecular collision. Formaldehyde is an early intermediate. Oxidation of formaldehyde gives the formyl radical, which then give carbon monoxide. Any resulting H2 oxidizes to H2O or other intermediates. Finally, the CO oxidizes, forming CO2. In the final stages, energy is transferred back to other third bodies. The overall speed of reaction is a function of the concentration of the various entities during the combustion process. The higher the temperature, the greater the concentration of radical species and the more rapid the combustion process. Reactions with halogens. Methane reacts with halogens given appropriate conditions as follows. X2 plus UV2XX plus CH4HX plus CH3CH3 plus X2CH3X plus X, where X is a halogen, fluorine, chlorine, bromine, or iodine. This mechanism for this process is called free radical halogenation. It is initiated with UV light or some other radical initiator. A chlorine atom is generated from elemental chlorine, which abstracts a hydrogen atom from methane, resulting in the formation of hydrogen chloride. The resulting methyl radical, CH3, can combine with another chlorine molecule to give methyl chloride and a chlorine atom. This chlorine atom can then react with another methane molecule, repeating the chlorination cycle. Similar reactions can produce dichloromethane, chloroform, and, ultimately, carbon tetrachloride, depending upon reaction conditions and the chlorine to methane ratio. Uses. Methane is used in industrial chemical processes and may be transported as a refrigerated liquid. While leaks from a refrigerated liquid container are initially heavier than air due to the increased density of the cold gas, the gas at ambient temperature is lighter than air. Gas pipelines distribute large amounts of natural gas, of which methane is the principal component. Fuel. Methane can be used as a gas for ovens, hobs, etc. It combusts with oxygen to create fire. Natural gas. Methane is important for electrical generation by burning it as a fuel in a gas turbine or steam generator. Compared to other hydrocarbon fuels, burning methane produces less carbon dioxide for each unit of heat released, at about 891 kilojoules per mole. Methane's heat of combustion is lower than any other hydrocarbon, but the ratio of the heat of combustion to the molecular mass shows that methane, being the simplest hydrocarbon, produces more heat per mass unit than other complex hydrocarbons. In many cities, methane is piped into homes for domestic heating and cooking purposes. In this context, it is usually known as natural gas, which is considered to have an energy content of 39 megajoules per cubic meter, or 1000 BTU per standard cubic foot. Methane in the form of compressed natural gas is used as a vehicle fuel and is claimed to be more environmentally friendly than other fossil fuels. such as gasoline, petrol and diesel. Research into adsorption methods of methane storage for use as an automotive fuel has been conducted. Liquefied natural gas. Liquefied natural gas is natural gas that has been converted to liquid form for ease of storage or transport. Liquefied natural gas takes up about 1/600th the volume of natural gas in the gaseous state. It is odorless, colorless, non-toxic and non-corrosive. Hazards include flammability after vaporization into a gaseous state, freezing and asphyxia. The liquefaction process involves removal of certain components, such as dust, acid gases, helium, water, and heavy hydrocarbons, which could cause difficulty downstream. The natural gas is then condensed into a liquid at close to atmospheric pressure by cooling it to approximately -162 degrees Celsius. LNG achieves a higher reduction in volume than compressed natural gas so that the energy density of LNG is 2.4 times greater than that of CNG or 60% of that of diesel fuel. This makes LNG cost-efficient to transport over long distances where pipelines do not exist. Specially designed cryogenic sea vessels or cryogenic road tankers are used for its transport. LNG, when it is not highly refined for special uses, is principally used for transporting natural gas to markets, where it is regasified and distributed as pipeline natural gas. It is also beginning to be used in LNG-fueled road vehicles. For example, trucks in commercial operation have been achieving payback periods of approximately 4 years on the higher initial investment required in LNG equipment on the trucks and LNG infrastructure to support fueling. However, it remains more common to design vehicles to use compressed natural gas. As of 2002, update. The relatively higher cost of LNG production and the need to store LNG in more expensive cryogenic tanks had slowed widespread commercial use. Power to gas. Power to gas is a technology which converts electrical power to a gas fuel. The method is used to convert carbon dioxide and water to methane, using electrolysis and the Sabatier reaction. The excess power or off-peak power generated by wind generators or solar arrays could theoretically be used for load balancing in the energy grid. Liquid methane rocket fuel in a highly refined form. Liquid methane is used as a rocket fuel. While investigations of methane use have existed for decades, no production methane engines have yet been used on orbital spaceflights. This is changing, and liquid methane has recently been selected for the active development of a variety of bipropellant rocket engines. Since the 1990s, a number of Russian rockets have been proposed to use liquid methane. One 1990s Russian engine proposal was the Rode 192, a methane LOX variant of the Rode 191. In 2005, U.S. companies, Orbitech and XCOR Aerospace, developed a demonstration liquid oxygen, liquid methane rocket engine and a larger 7,500 pounds force thrust engine in 2007 for potential use as the CEV lunar return engine, before the CEV program was later cancelled. More recently, the American private space company SpaceX announced in 2012 an initiative to develop liquid methane rocket engines, including, initially, the Very Large Raptor rocket engine. Raptor is being designed to produce 4.4 meganewtons of thrust with a vacuum-specific impulse of 363 seconds and a sea-level ISP of 321 seconds, and is expected to begin component-level testing in 2014. In February 2014, the Raptor engine design was revealed to be of the highly efficient and theoretically more reliable full-flow staged combustion cycle type, where both propellant streams, oxidizer and fuel, will be completely in the gas phase before they enter the combustion chamber. Prior to 2014, only 2 full-flow rocket engines have ever progressed sufficiently to be tested on test stands. but neither engine completed development or flew on a flight vehicle. In October 2013, the China Aerospace Science and Technology Corporation, a state-owned contractor for the Chinese space program, announced that it had completed a first ignition test on a new LOX methane rocket engine. No engine size was provided. In September 2014, another American private space company, Blue Origin, publicly announced that they were into their third year of development work on a large methane rocket engine. The new engine, the Blue Engine 4, or B4, has been designed to produce 2,400 kilonewtons of thrust. While initially planned to be used exclusively on a Blue Origin proprietary launch vehicle, it will now be used on a new United Launch Alliance engine on a new launch vehicle that is a successor to the Atlas V. ULA indicated in 2014 that they will make the maiden flight of the new launch vehicle no earlier than 2019. One advantage of methane is that it is abundant in many parts of the solar system and it could potentially be harvested on the surface of another solar system body, providing fuel for a return journey. By 2013, NASA's Project Morpheus had developed a small restartable LOX methane rocket engine with 5,000 pounds force thrust and a specific impulse of 321 seconds suitable for in-space applications including landers. Small LOX methane thrusters 5 to 15 pounds force were also developed suitable for use in a reaction control system. Space News is reporting in early 2015 that the French space agency CNES is working with Germany and a few other governments and will propose a LOX methane engine on a reusable launch vehicle by mid-2015, with flight testing unlikely before approximately 2026. Chemical feedstock. Although there is great interest in converting methane into useful or more easily liquefied compounds, the only practical processes are relatively unselective. In the chemical industry, methane is converted to synthesis gas, a mixture of carbon monoxide and hydrogen, by steam reforming. This endergonic process utilizes nickel catalysts and requires high temperatures, around 700 to 1100 degrees Celsius. CH4 plus H2O CO plus 3H2 related chemistries are exploited in the Haber-Bosch synthesis of ammonia from air, which is reduced with natural gas to a mixture of carbon dioxide, water, and ammonia. Methane is also subjected to free radical chlorination in the production of chloromethanes, although methanol is a more typical precursor. Production. Biological routes. Naturally occurring methane is mainly produced by the process of methanogenesis. This multi-step process is used by microorganisms as an energy source. The net reaction is CO2 plus 8H plus AT minus CH4 plus 2H2O. The final step in the process is catalyzed by the enzyme coenzyme B-sulfoethyldeotransferase. Methanogenesis is a form of anaerobic respiration used by organisms that occupy landfill, ruminants, and the guts of termites. It is uncertain if plants are a source of methane emissions. Serpentinization. Methane could also be produced by a non-biological process called serpentinization involving water, carbon dioxide, and the mineral olivine, which is known to be common on Mars. Industrial routes. Methane can be produced by hydrogenating carbon dioxide through the Sabatier process. Methane is also a side product of the hydrogenation of carbon monoxide in the Fischer-Tropsch process. This technology is practiced on a large scale to produce longer chain molecules than methane. Natural gas is so abundant that the intentional production of methane is relatively rare. The only large-scale facility of this kind is the Great Plains Synfuels plant, started in 1984 in Beulah, North Dakota as a way to develop abundant local resources of low-grade lignite, a resource which is otherwise very hard to transport for its weight, ash content, low calorific value and propensity to spontaneous combustion during storage and transport. An adaptation of the Sabatier methanation reaction may be used via a mixed catalyst bed and a reverse water-gas shift in a single reactor to produce methane from the raw materials available on Mars. Utilizing water from the Martian subsoil and carbon dioxide in the Martian atmosphere. Laboratory synthesis. Methane can also be produced by the destructive distillation of acetic acid in the presence of soda lime or similar. Acetic acid is decarboxylated in this process. Methane can also be prepared by reaction of aluminium carbide with water or strong acids.